fly. The midnight train is winding low, and I'm so lonesome I could cry. Have you ever seen a robin weep when leaves begin to die? That means he's lost the will to live, and I'm so lonesome I could cry. The silence of a falling star lights up a purple sky. The moon just went behind the clouds to hide its face and cry. Well, I never seen a night so long when time comes crawling by. And as I wonder where you are, I'm so lonesome I could cry. No, I never seen a night so long when time comes crawling by. And as I wonder where you are, I'm so lonesome I could cry. I'm so lonesome I could cry.
All right, welcome back. Today we're going to finish up talking about arrays by looking at a few miscellaneous items and concluding with multidimensional arrays. In particular, we're only going to probably look at two-dimensional arrays, also known as tables with rows and columns, or matrices. Right? So I wanted to finish up on the demonstration that we were doing last time before we continue with those items. Remember that we wrote a function that creates a new array of integers, initialized all to zeros. We called that the zeros array. The return type was an integer pointer, and it took an integer and the size of the new array, and it called malloc to create enough space to hold that. And then, of course, it had to go through and initialize those all to 0, because there's no guarantee that the default value in an array in C is going to be 0. Now, in our demonstrations, that turned out to be the case, but it's not always going to be the case. That is completely dependent on the compiler and the system that you're using. Right? But ultimately, we return this array. And when we received it back over here, we were able to iterate through it. And we knew the size because we asked for a size. If I said, I want an array filled with zeros of size 10, and I give you that value, of course, we both know that I want, that I want an array of size 10, right? Now, in the second one, write a function that returns a new array containing only even integers of a given array. So what we mean by that is, we initially wrote this documentation here. This function takes an array of integers and returns a new array filled with only the even values from that array. So down here, I've got a test vector right here, this test array, 2, 3, 4, 6, 10, et cetera, et cetera. If I give this to this evens array, then I would expect 2, but not 3, 4, 6, 10, 4, 2, but not 3 again, not 1, but I wouldn't expect 4, right? So how big is that new array? Well, the old array was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For this particular example, I know that I would end up excluding 3 of these things. So the new array of size is 7. Now, if the calling function, main here, knew that, well, then it could do the work itself. All I want to do is I want to give you this array, the size of the array, and then I want you to give me a new array of a particular size. The size of the resulting array is communicated not through the return type, because that's going to be the new array, right? We're stuck. We can't return a pointer easily with a pass by reference value. You can do it, but what you need is what we're going to look at the end of the day. You need a pointer to a pointer, right? In order to be able to do that. So we're going to take this approach right here. I'm going to give you an array and its size, and I'm going to give you a bucket. So you're going to give me back an array filled with those 7 even numbers, and in this bucket, you're going to put the value 7 because that's the size of the resulting array. I can then look in this bucket to determine how big is this array that you gave back to me, right? And I can only do that through a return, a pass by reference variable right here, okay? So we ended last time on saying, okay, well, I don't know how to do this and I don't have time to do this, so we'll do it later. Help me out, suggestions. Remember, we are on Piazza, so if you've got questions, make sure that you're posting to Piazza. So any suggestions on how to get started on this? Yeah.
For loop that goes through the array and has an integer and just adds every time it grabs a positive.
All right. An even number, right? To determine how big of a new array you need, right? So I'll put that onto 2 lines here, right? 1, iterate through the array to determine how big of an array you need. So I'm just going to go ahead and establish a variable called count, initialize it to 0, right? Because it could be that there are no evens in this, in which case that's fine, right? Go ahead and return an array of size 0, or, oh wait, what if they give me null? What if they give me a bad size? So maybe as step 0, what should I do doing? Error checking, all right? So error checking if array is null, they gave me a bad array, or if n is less than or equal to 0, or you could say that, well, if a negatively sized array, that's bad. But an array of size 0, maybe that's fine. I'll give you an array of size 0. Or you could say, no, that doesn't make sense to me, right? That's all a design decision that you need to make, right? So I'll go ahead and say that a 0-sized array is an error in this case. If that's the case, or what else could be wrong here? What else could, so I error check this, well, certainly null. 0 or negative, that's bad. What about this one? Null pointer check there as well. If that's null, then return what? What's the only thing that I can return here? I have to return a pointer. So what is a pointer value that says this is wrong? Something bad happened. You gave me bad input. Return null. Just like malloc does. If malloc cannot allocate enough memory for your use, then it returns null, indicating a null pointer. Sorry, I can't allocate that 100 million terabytes that you asked for. Okay, Good. So now let's go ahead and go through and iterate to determine how big of an array size you need. For int I equals 0, I is less than n. There's that idiomatic for loop again, where you iterate over elements of an array of size n. If array of I mod 2 is 0, indicating that it's even, then I need to add it. Now, I could in some way, you know, on the fly add elements to the array, but then that would require me setting that up first, so I would have to know upfront a priori how big of an array size you need. Or I could do something hackish like just create a big size array that could hold everything potentially, fill it up as much as you can, and then waste this space. That's kind of bad. Or fill it up as much as you can with temporary space and then say, okay, well, I only needed an array this size. Go ahead and create a new array, copy everything over, then delete this array. Right? There are lots of ways that you could do this. I don't see a reason for doing that if you have to iterate over it twice anyway. Right? So I'll go ahead and iterate over it once, count up the number of slots you need. Now, to allocate memory for the new array. So that's going to be a call to malloc. Result is equal to int star, because we are typecasting the void pointer that malloc gives us back. Malloc only gives us a raw memory address. It can point to anything. It can point to a memory address that holds integers. It can point to a memory address that holds doubles. What I'm doing by typecasting a call to malloc is I'm forcing it to point to a memory location that holds integers, right? Because that is my return type right here, okay? How big of an array do you need? Well, count times how many bytes does an integer take? 4. But is that the right way of doing it? Nope. Size of an integer, because that will make it more portable. If you move to a system where an integer is now suddenly of size 2 bytes, then it'll still work. And ultimately, that's what you're going to return. So I'll go ahead and say return result. Right? But before we do that, of course, we have to fill up the result array with the actual even values. There we go. So 2. Copy over the even values. Right? So I'm going to go ahead and go into another idiomatic for loop here. Right? For each element in the array that I was given, ARR, if, in fact, I should have just copied this too. Right? There we go. If it's even, then instead of adding a counter here, I'll say result of something is equal to array of I. Right? Now, what is this something right here? So if I go and I keep an index iterating over this input array, 0, 1, 2, 3, 4. That's I. I is 0. I 1, 2, 3, 4, 5, etc., etc. I'll copy this one over, fine. But when I get to this one, I is now 1, but I don't copy it over. I just move on to 2. Right? Should I move on in the copy of the array? Nope. So I want to maintain another index variable here. And I'll just say int. We could call it j. But I'll go ahead and call it index. Where should I start it? 0, right? And I will use it down here, right? So that I will now have 2 independent indices. I is for the input array. Index, or j if you wanted to call it that, is for the output array. If it's even, I will copy it over and move both of these indices over. If it's odd, just this index gets moved over. This one stays the same, right? So if it's even, I copy it and move my index over. The input index here is being taken care of by the for loop up here anyway. So I don't have to do anything with that. Right? Am I done? All right, well, maybe not. Maybe not. Let's go ahead and go down here to main and see and test it, right? You guys have been doing a lot of testing recently. Why? Well, you need at least a sanity check. You at least need one test to make sure that it actually works, right? Or that it gives you at least a little bit of confidence that it works. I would expect back an array of size 7 having 2, 4, 6, 10, 4, 2, and 4, right? So I will pass in BRR the size of the array, which was what, 10? Right? And what about the size of the resulting array? New size. Int new size. There we go. So that down here, if I'm going to iterate over and print out each one of these in that resulting array, I need to know how big of an array I have now, right? Is this how I pass in a variable by reference? Nope. In fact, let's go ahead and try to compile this. It's even telling me int star, but of type, it's an element of type int, right? Right here on the third argument. This is up here. This is a pointer. New size down here is not a pointer. How do I make it into a pointer? Ampersand. Right? Hey, it compiles. Let's make sure. Okay, no warnings. Is this going to run? Whoa, it went for 10. Why? Oh, wait, you know what? Oh, that's this print up here. I should be seeing B evens down here, shouldn't I? After this initial print. In fact, if you want to get rid of this, there we go. Unused. Don't worry about that. I just printed it out. Oh, there we go. Now it's screwing up even worse. What's happening here? It's a size 32,600 and some, or 32,763. If I run this again, I get, it's going to run the same way here. What size is new size here? Is that ever set up here? We check to see if it's null. We create a new variable to see how big the new array is. We allocate the memory for the new array. We copy over the even values, but what did we not do? We need to set new size to count. Why? Because I need to now I need to fill the bucket. I've got your array here full of even integers, but now I need to fill the bucket to tell you that there are only 7 of them. Okay? So is this the way that I do it? New size is equal to, well, 7. That's definitely not the way. It's count, first of all. But new size is what type of variable? A pointer. To set its value, I have to change the pointer into a regular old variable. So I can star to dereference it. Now, what you could have done alternatively is, I don't need another variable here. I could have just said, use new counter, and then instead of going new count, I could have gone new count, or what was it, new in size plus plus. That's not going to work. That's not going to work because I believe plus plus has a higher order of precedence than the dereferencing operator. If you're going to do something like this, then you have to write even more code to force the dereference to happen first and then plus plus. I don't like doing that. Right? I don't like having to think about the whole order of precedence. PEMDAS is hard enough to keep in your head. Don't worry about all that other crap. Right? Just create another variable, and it's perfectly fine. Right? Set it once down here instead. Okay? Now when I do this, hopefully it'll work. There, now there are only 7. And they're exactly the ones I wanted. 2, 4, 6, 10, 4, 2, and 4. Excellent. Right. I will make sure that you have this in the notes. There you go. All right. So other issues here. First of all, pointer arithmetic. The square bracket syntax is actually syntactic sugar for pointer arithmetic. Right? So syntactic sugar, what that might hopefully that's a term I've used before, but in any case, what it means is syntactic sugar is it's extra. It's extra syntax. Like plus plus, we don't need plus plus. We could just say I is equal to I plus 1 every single time if we really wanted to. Plus plus is syntactic sugar that allows us to do that in a little bit shorter way. It's like having 50 different words to describe good instead of just one word to describe good. You want variety. You want sugar in your language, right? You want extra in your language so that you can shorthand stuff, make it more terse, make it more readily understandable. As long as you learn this stuff up front. Plus is so much easier to look at and immediately understand than is I is equal to I plus 1. It's also quicker to write, right? Syntactic sugar is a way that you can shorthand things. If we didn't have the square bracket syntax, basically what we would have to do is we'd have to do our own arithmetic. When passing an array to a function, no ampersand is necessary. Why? Because the name of a function, regardless of how you've created it, if it's a static function, it's a dynamic function, it doesn't matter. Not a function. The name of an array is its memory address. Right? So if I take, if for example up here, if I take b evens, well, obviously that's a memory address. But BRR right here, even though I've created this statically, BRR is a memory address. It's already a pointer, right? So the name of an array is already a memory address. It is already a pointer. So no need to change it into a pointer, right? By default, all arrays are passed by reference, right? So consequently, without the here, not consequently, but if we lived in a world without that square bracket notation, without the square brackets, we'd have to determine which memory location the second element is at, the third, etc. Right? For example, or the first element is at memory location ARR. Suppose that we've got an array called ARR. Okay, the first memory location is at ARR, or in square bracket notation, ARR sub 0, i.e. 0 bytes away from ARR. Right? Or equivalently, ARR plus 0. Okay. Where's the second element? The second element is 4 bytes, assuming an integer array. Right? So maybe I'll put that up at the top. Suppose we have an integer array, ARR. Right? The second element is at 4 bytes away. Right? So ARR, so plus 4. Right? The third element is 8 bytes away, or ARR plus 8. Or in general, the ith element is I times 4. Well, here, I'll do it code-wise here. I times 4 bytes away. There we go. Array plus 4 times I. Something like that. Right? Or equivalently, if you want to make it as general as possible, it's going to be ARR plus size of int times I. Right? Now, do you really want to do that arithmetic all by yourself? Imagine if you had to do something like this every single time you wanted to access the ith element. Right? This is why we have convenient. It is far more convenient to write, ARR sub 0 for the first one, ARR sub 1 for the second one, ARR sub 2 for the third one, and in general, ARR sub I. Right? But it is important to understand that that's how it works. And this is why we have 0 indexing to begin with. Right? Mathematicians, in math, you always start your indexing at 1, generally. But in computer science, all of our stuff begins at 0. Why? Because ultimately everything is a memory address. And so why jump 4 bytes away immediately? Why waste that space? The first one is at index 0. Then the second one is index 1 times however many bytes away it is. If this were a double array instead of an integer array, then of course we would be 8 bytes away, 16 bytes away, or in general, size of double times I, okay? Now, there is an instance in which you do have to do this pointer arithmetic that we'll look at much later on. It's when you use raw types, when you're actually, when you do use a void pointer, and you don't know what you've been given. Here's an array. What's an array of? I don't know, it doesn't matter, right? I'm telling you to do this other operation. You don't need to know that kind of thing, all right? For example, searching and sorting. That's exactly what searching and sorting algorithms do. Here's this array. Well, what's in there? I'm not going to tell you. Okay, well, how do I sort it? Oh, here's another thing over here that if you pull 2 elements out of it, it tells you that this one goes first and this one goes second, or the other way around, or they're equal. That means that well, I know how to swap those if they're out of order. I know how to leave them alone if they're in order. Right? I don't need to know that it's integers. I don't need to know that they're doubles. I don't need to know that they are student structures, which we'll eventually get into with structures later on. That way you can write one function to sort stuff and never have to worry about that problem again. Right? You don't have to have a function to sort integers and another one to sort doubles and another one to sort whatever. Right? You just write one function. In fact, it's already written for you. Right? All right, that's pointer arithmetic, but it also solves the mystery of why is everything 0 indexed in computer science? And it's because of how memory works. Right? The other thing that I wanted to go over was consts. All right, here we go. So, constant arrays. So what I'm going to do to motivate this is let's go back over here and go back to our, let's go back to our get evens. Did I make any changes to ARR up here? The original array? You gave me an array. I went through and made a copy of it and then gave that copy back to you. Did I touch the original? No. Should I have touched the original? Probably not. But let's try. Right? So what we'll do is we'll go through, and if it's even, then we'll increase our counter. Else, we'll go ahead and do something stupid like ARR sub I is equal to 42. Right? Why on earth would I go through and reset all of your odd numbers to 42? Right? I wouldn't. I'm being malicious here. I'm screwing up your data, right? But it's perfectly fine to do so. Now it's not going to be apparent here because I'm not printing it out, but let's go ahead and do that. Copy, put it down here. There we go. And you can see here that, oops, they're all zeros. Oh, sorry. No, the original is what? BRR. BRR and BRR. There we go. There we go. I changed those 3 even odd numbers into 42s. I changed your 3 into a 42. I changed your other 3 into a 42. And I changed your 1 into a 42. Why are you changing my stuff, man? I just gave it to you to give me a copy of that, right? So we should be able to prevent something like this, right? If you don't want a function to make changes to your array, you can declare it as const or constant, right? This makes your array nearly read-only, right? There are ways around this. It's not like a security thing that this will absolutely work every single time. There are ways that you can get around this. But at least the compiler can check at least a rudimentary check on this. So what I mean by that is let's go back up here to our function signature and declare this as const. It's a constant integer pointer, meaning that you cannot change this, okay? Now, I am still changing it down here, so let's find out what happens. Right. Error. Assignment of a read-only location is done on this line right here. The compiler can check. I made a promise here that I was not going to change this. The compiler found me out that, hey, indeed you are changing this. I'm going to refuse to compile this. Okay, fine. I won't be malicious anymore. Right? When I do that, just the warning remains. The compiler error is now gone. And now I'm no longer able to, I can't change your stuff, right? Well, after compilation. Of course, there are underhanded ways of doing it, but we won't go over those, right? Basically, just copy it to another pointer that's not constant and then modify it through, surreptitiously through another pointer, right? But then why are you being malicious? You're the one that said that you were const to begin with, right? So that makes everything nearly read-only, right? Attempts to change a const array can be detected by the compiler, and it results in a compiler error. In general, every function, any function that does not make changes to an array should declare them as const. Right? You should always use the const keyword unless you are going to make changes. In fact, that's such a best practice that if you see that an array is not const, you should just make the assumption that it's going to be changed. Period. Right? So, in general, non-const arrays are assumed to be changed by the function, by a function, whatever. Right? That is just that's just the best. That's the normal practice. So if you look at any function in the standard library and you see that it takes an array and there's no const in front of it, oh, it's going to change it, right? So if you don't want it being changed, then you need to do something else, right? And is that the next thing we're talking about? Yep. All right. So here's another motivation. Demo, or shallow versus deep copies. Okay. All right. For this, I'm going to go back over here to the C visualization thing. And what I'm going to do is I'm going to create an integer array, A. I'll just call it A for short here. Make a call to malloc, int star, malloc. How many? Well, we'll just make it n, and we'll set it n to be small here. Int n is equal to 5, and size of int. There we go. And then we'll go ahead and fill it up with numbers. For int I equals 0, I is less than 5, n, I plus plus. A sub I is equal to I plus 1. So I'm going to fill it up with 1, 2, 3, 4, 5. Okay? And then we can print it out down here. Printf a sub %d is equal to %d and the line I and a sub I. Now this is nothing special. We've done this before, so I'm not going to visualize this code. But what I am going to do is I'm going to make what's called a shallow copy. Int b is equal to a. Right? At the same time, let's go ahead and print both of these things out, b and b. Well, if I'm setting b to equal a, what would you expect here? It would be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? You'd expect the same things, okay? So let's go ahead and visualize this execution. While we're waiting on that to churn, let me come back over here and show you its actual execution. This will save us some time when we look at the visualization. 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. What happens when I try to change one of them? So let's go ahead and change a sub 0 to be 42 and try to print them out all again. Let's see. All right, there we go. So next, 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 right? Next, next, fills up with 1, 2, 3, 4, 5. All right, we're good. Now what's going to happen on line 9? Is that going to be its own array? Nope. 2 pointers are pointing to the same thing. Right? So when I print them out, of course, it's going to print out that they're all the same. 2, 2, 3, 3, 4, 4, etc. What if I change one of them? What if I change A? Is that change going to be reflected in B or not? So let's clear this out and CCC and run it again. Uh-oh. A sub 0 is 42, as I specified, but also B sub 0 is 42. Why? Let's go back over to the visualization, edit this, and change. I'll just change it right here. Right? And let's see. Because those two pointers were pointing to the same thing, changes to one are reflected in the other. There we go. Fly through this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. B is pointing to this. So when A is changed, well, what is B pointing to? The exact same thing. So when we print it out again, it's going to end up being 42. Both of those are 42. Okay? This is known as a shallow copy. Right? When references are copied, they are only shallow copies. Right? Changes to an array through one reference are seen by the second reference, right? By the second pointer, basically. Right? Alternatively, if you want a totally distinct copy, you want a deep copy. Right? In other words, you want two completely different arrays stored in two completely different memory addresses. Right? Let's go back over here. Let's go back over here to this code right here. And again, let's label this as a shallow copy. Right? We're only copying the pointers so that the pointers are pointing to the same thing. That's not what I want. I want a copy so that A points to its own copy, B points to its own copy, so that when I change this one to 42, this one stays as 1. Right? Because if I'm going to hand this over to a function that's going to be making changes to it, but I want to retain the original data, then I need to make a deep copy, hand over that copy to the function so that it doesn't screw up my original data. Okay? How do we go about doing that? Well, that sounds like a job for a function. Right? This function makes a deep copy of the given array. Right? Period. All right, well, we'll just keep it as integers. So if it's returning a new integer array, it should be int star. What should I call this function? I could call it copy, but I'll call it, what kind of copy is it? Is it shallow copy, or is it copy, or is it a deep copy? Okay, deep copy. And if it's 2 words, you can go deep copy there. Okay. What does it take as input? An array, and we'll just call it A in this case. And of course, what else do you need to give a function if you're giving an array? The size of the array, int n. Right? But am I going to be making changes to the original? No. So what should I do? Const. Do I need to tell the calling function, now I'm the function here, do I need to tell you how big of an array you have, or the result is? If I'm making a deep copy, you gave me an array of 10 elements, I'm going to give you back an array of 10 elements. Do I need to also tell you that it's 10 elements? No, you told me that it was 10 elements through this variable right here. So you should know that, right? So we don't need to do a trick like we did up here with the new size. Okay? Well, how might I go about writing this function? Okay, do some basic error checking for that copy pasta, but don't do that. So if A is null or n is less than or equal to 0, then we can return null. You gave me null, I'm going to give you a copy of null. Yeah, right? Fine. Otherwise, we will create a new array of the given size. I can't call it A, so I'll call it C for copy. And return C. Is that enough? Nope. What do I need to do? I need to actually copy each element over. So for int I equals 0, I is less than n, I plus plus, idiomatic for loop here. C sub I is equal to A sub I. And now that's going to be a deep copy. So let's go down here and make sure that it actually works. Instead of doing that, I will do a deep copy by calling deep copy of on A and of size, what size is A? N. There we go. Oh, no, I do want to keep that. So that when I change A, now that change will no longer be reflected in B. Okay? Let's run this again. Oops. Misspelled right here. There we go. All right, and run this. And now you'll see that, oops, where are we? Clear. There we go. A, B. There we go. Oh, what's wrong? B is equal to deep copy. I change A to 42. Let's get rid of this. That looks good. B is equal to deep copy. I did everything right, right? C is equal to A sub I, and then return C. I receive it down here. A sub 0 is equal to 42. Oh, yeah, this is right. But I was just looking at the wrong lines. We've got 42 here for A, and B still retains its value of 1. Okay? So if you want to see what that looks like over here in the C tutor visualization, we can go ahead and try it. Let's change this to that. And then we do need to copy over that function. I'll just copy over the function, not the documentation. There we go. And let's try to visualize this. Fine. Include stdlib.h. That's where null is defined. So visualize that. B is in, int star B. There you go. Come on. So I must have fixed everything because now it's taking forever, right? And come on, close that. Now we can go ahead and walk through this code. So there's 1, 2, 3, 4, 5. Right? And then we call deep copy, right? Deep copy is going to make a reference to the original, but you can see now that C is pointing to a completely different copy. Now there are 2 arrays in memory. Once we copy everything over, B receives that original, that new pointer, and now we've got 2 distinct copies so that when we change A sub 0 to 42, B sub 0 is unchanged. Excellent. Okay? So when would you want to use this? Use deep copies when you don't want changes to the original. Right? Or you need to make changes because you need to process it, but you want to retain the original data. Or you want to retain the original data. Okay, excellent. Last thing of the day for the miscellaneous roundup here would be multidimensional arrays, right? Or we're just going to go with 2D arrays. You can go with higher dimensional arrays, but there's really no point. You can always have arrays with more than one dimension. Right? Now, when we say dimension, it does kind of mean kind of like the dimensions that you're used to. 1 dimensional would be on the number line. 2 dimensions would be X and Y. So in other words, a table, right? So 1 dimension, 1D arrays are regular old arrays. 2D arrays have rows and columns, right? So you can think of these as tables or matrices, right? If you've ever had any matrix theory. Matrix theory is just a table, right? You've got a certain number of rows and a certain number of columns, and then you've got numbers in those rows and columns in each one of those cells. Just think of it as a table, right? Otherwise, you can also have 3D arrays where you have rows, columns, and the third dimension, we call those aisles, right? Just like in, if you go to a regular old grocery store, guess what? You're in the third dimension. And you've got rows, you've got columns of cereal boxes and rows of cereal boxes, but you also walk down the aisle, that's your third dimension, because we're three-dimensional beings, right? Or lanes, right? You can also have 4D arrays, but then the analogy falls apart. Nah, right? Don't do that. In fact, the 3D arrays pretty much are not advisable. If you find yourself going 3 dimensions or 4 dimensions or 5 dimensions or 6 dimensions, rethink what you're doing, right? You probably need, you would probably be better suited to create what's called a structure. That's something that we'll look at later on, okay? In general, limit consideration to 2D arrays at most, right? If you find yourself needing more arrays, then use a structure. In C, a pointer, int star array, points to a 1D array. Right? So consequently, an int star, and I'll call it M here, or mat for matrix, or T for table, whatever you want, points to a 2D array. Right? So 1 star for 1 dimension, 2 stars for 2 dimensions. How does that work, right? Essentially, the star points to an array of integers, or of pointers, excuse me, right? Each pointer in the array points to its own 1D array. In that way, we've got an entire array of pointers, and each one of those pointers points to a row in the table or the matrix, okay? So all we need to do is set it up properly to set up a two-dimensional array. For that, I'm initially going to go over here to this code visualization tool so that we can actually see what's going on, okay? Go ahead and get rid of this deep copy stuff. And what I'm going to do is I'm going to make a 3 by 2 array, int m. It doesn't have to be square. I think in your assignments, no, it definitely is not. In your hack on Thursday, you'll be working with two-dimensional arrays. Each one of the things is not a number, but a pixel. So in other words, you'll be working with images. And then you can flip an image. You can rotate an image. Basically, by taking this table and rotating the table, or taking this first pixel over here and this last pixel, exchanging them. Second pixel, second to last pixel, exchange them. Do that for each row, and what have you done? You flipped the picture. Right? So you're actually going to start manipulating media with this kind of stuff. And the way that you can look at a picture is you've got rows of pixels and columns of pixels. Right? Simple enough. So you don't need to, so this one will be a 3 by 2, in other words, 3 rows, right? And 2 columns. How many elements in total? 6, right? In general, if it's n rows and m columns, we call that row major form, where the rows come first and then the columns comes second. You will have an n by m array, okay? So let's get rid of all this stuff. There we go. How do I set myself up? Well, I'll go ahead and create an integer array of 2 dimensions. I'll just call it MAT, short for matrix, right? And it's going to be a call to malloc. Now remember, visually, ultimately what this is going to look like is we've got an array of integers, and each one of those integers is, if I'm going to take this array and transpose it basically by putting it as a vertical array now. Each one of these pointers is going to point to another array that's, each one is a row, basically. So how do I typecast this? The typecast always matches the variable on the left-hand side. So That's no big deal. You want an array of pointers of 1, 2, 3 pointers to point to 1, 2, 3 rows. Okay. I want n of them. Size of, what goes in here now, though? Think about what's stored in this array that I'm alluding to here. It's a pointer that points to an integer. So is it going to take the same number of bytes as an integer, 4 bytes? Maybe, maybe not. But that's not the correct way of doing it. If each one of these things is a integer pointer, that's not an integer pointer. That's just a integer. How do I make this into an integer pointer? For the type, it's an int star. Oop. There. Keep thinking I'm in the IDE to save all the time. That sets up, in fact, let's see if we can visualize this before we move on. Yeah, there we go. It was simple enough. So we've got 3 by 2. Now matrix is pointing to, this is not a number in here. This is now a pointer. Each one of these pointers is going to point to a new row of size 2. How do we do that? Well, if you want to do this multiple times, then you need to write a loop to do it. I is equal to 0, I is less than n, I plus plus. Mat, sorry, of I is equal to, now mats of I is just a regular old integer pointer. So we would call malloc like we've been doing up to this point. Int star, malloc, you want m of them times size of, and now this is a regular old integer, not an integer pointer. This is just going to create one row of m integers, okay? What's in there? Let's visualize this before we actually do anything with it. I don't know if they use poop emojis or not, but let's go ahead and find out. So once we set up the initial row, then this for loop is going to set up this pointer, then this pointer, then this pointer. Each one of those is going to end up being an array of size 2. Size 2, size 2. So I have a 3 by 2 dimensional matrix. Now there are alternative ways of doing this, a couple of alternative ways of doing this. If you read my textbook, then you can basically you can create a big giant contiguous chunk of memory and then set up the pointers appropriately to make it, to treat it like a two-dimensional matrix, but you only really have one dimensions. So all of your, here's a row, then right next to it is the next row, then right next to it is another row. But there are several different ways of doing this. If you want to check them out, then check out the my textbook, not Zai books. Right? There's a little subsection in there on alternative ways of doing this. Once we've set this up, we can treat it like a regular old two-dimensional matrix. The way that we can set values is by providing 2 square bracket notations here. If I want to set the first, the one in the first row in the first column, that would be at 0, 0. I can set that equal to 42. If I want to set the element in the first column, first row, second column, then I can set that equal to 101. Right? I can set the second row, first column to whatever, or give me something. 3, okay. 20? Okay. I don't know whose numbers these are. Husker numbers. Husker numbers? I haven't watched the game yet, so I don't know who. I forget all the numbers from last year. But anyway, I don't know. Bryant is back on track, and I don't know. Well, he may be retiring, or at least from the Cubs, so let's go with Lester. There we go. Cubs players instead. So, come on. Okay. Well, usually it goes right after this, but if not, then yeah, there we go. All right. Next, next, next. Once we set up each one of these rows like we did last time, right? They're all uninitialized, which is why they've got question marks. But when we come down here and start initializing things, The first row, first column gets set equal to 42. Second row, first row, second column gets set equal to 101, right? And so on and so on. 3, 20, 17, and 34. What happens if we go beyond the number of rows? What happens if we go beyond the number of columns? Undefined behavior, and you may or may not end up with a segmentation fault. Right? Now, idiomatic for loops with respect to this means that you've got 2 for loops. Right? Let's go ahead and now print these out. Right? Print out the matrix. Right? For int I equals 0, I is less than n, I plus plus. In other words, for each row, right? Dot, dot, dot. Then inside that for loop, we need to go for each column. For int j, starting at 0, j is less than m, because there are m columns up here, j plus plus. And again, this is for each column in row I, dot, dot, dot. We can do whatever we want with it. So printf %d space, and I'll print out mat of I, j. Remember, 2 dimensions because it's a 2-dimensional array. Right? Now, just to make it look pretty, at the end of each row, I will print an n-line character so that it goes down to the next row. And then we can see, I'm no longer going to visualize this since it's not necessary. Instead, let's go ahead and take it over here. I've got all this in the notes, I think. If not, I can put it there. There we go. All right. Oops, save it. Don't worry about that. We've got include stdlib.h include stdio.h. There we go. Now you won't complain anymore. All right. Run that. And there we got 42, 101, 3, 20, 17, and 34. If you want to clean that up a little bit, you can. Go ahead and make sure that everything's aligned. You can put nice little square brackets at the beginning and the end. Printf, square bracket, space. And that'll nicely format everything into what looks like a matrix, right? With ASCII text art around it. Right? Any questions on that so far? How do you comment out multiple lines of code like that? A good question. You probably saw me do something like this, block. Like, I don't care about this right now. I want to get rid of this. Right? Comment, uncomment, comment, uncomment. Right? How do you do it with multiple lines? Most IDEs will support that. Well, all you need to do is select what you want to comment out, and then to block to do it on a Mac, it's going to be command and then /. Right? Yeah, that's /. And in other words, the same one that you would use to comment or make a comment. To get rid of it, of course, you just do the same thing again. If you're on Windows, tell me, because on Mac it's command /. I bought my first Windows machine this last weekend in 10 years, so I haven't tried it out yet, though. So I don't know what it is. Probably, I would guess, Control. All right, Control / would do it on Windows. Go ahead and experiment and see what works. Or Control or maybe Alt or Window Window / or something like that. Control / is confirmed. Thank you. All right. One last thing on this, though. But what happens when you need to clean up? Clean up. Right. Now, for this, I will go over here to this this visualization. Forget about printing them out. Right. How do I free things up again? Free mat. Okay. Let's visualize this execution and find out what happens here. All right. Next. Blah, blah, blah. I never set these things, but that doesn't matter. I'm about to free it up. But what am I about to free up? I'm about to free up mat. In other words, this thing right here. What happens when I free that up? What happens to these 1, 2, 3 pointers? Those 3 pointers are gone. But what happens to the memory space down here? It still exists. It still belongs to my program. but I lose all references to it. I wonder what it visualizes it as, right? Well, that gets cleaned up, but it shouldn't have deleted those. It should have shown you that that in fact is a memory leak, right? I've got now memory that belongs to me. I'm holding on to it, but I've lost references to it, so I can no longer free it up. Consequently, it is wasted memory that can never be reclaimed until my program dies, in which case the operating system reclaims everything back. Okay? So, how do you address this? You go backwards. If I created the array of pointers to be first, and then for each pointer I created a new array of integers, I need to work in the reverse. I need to clean up each one of those and then clean up the matrix. Free up each row first, ... So the way that I do that is simply free the ith row. And once I do that, no more saving. Visualize this execution. There we go. So let's run through it. Sets up those three things. Now I'm about to free the first one. Well, one more step. In fact, let's zoom out. No, I can't zoom out. There, I zoomed out there. Right? Now it's the poop emoji again because it's been freed up. Right? Second one gets freed up. Third one gets freed up. Now those things are no longer memory leaks because they've all been freed. But I'm now free to free up the array of pointers here. And now that's a poop emoji because it's been freed up. Okay? Again, once you free memory, you cannot access it anymore. Accessing it is undefined behavior. It might work, it might not. It probably won't give you the results that you're looking for. It might result in a segmentation fault. It could any number of things could happen. But when you free it up, you need to free it up in reverse, right? So edit this code so that I've got it over here as well. And I'll make sure that all of this is in the notes. All the way to the top. There we go. All right, so demo. See. All right. Any questions so far on this? Okay. Then what about arrays of char values? Right. So far, I've really only done integers for demonstration purposes, but of course you could do doubles very easily. On Thursday with your hack, you'll be doing pixels, right? Which have RGB values to them, the way that we set it up, I think that we made it all completely opaque. So RGB values can also have red, green, and blue, and also what is it called for transparency? Say opacity. Thank you. The opposite of transparent, opacity, where 1 means that it is completely opaque, and 0 means it's completely transparent, and 50% means that whatever's behind it will bleed through it, right? I think that what we just made it all completely opaque, but if you want to, you can start hacking the code and make little transparencies if you really want to. So transparent GIFs or PNGs or whatever. Not all formats support transparencies. That's why we went with that. But each one of those pixels will have an RGB value, and then you can flip them around. You can flip them around and then do crazy things with it. But the two-dimensional array exercises that we give you are basically flipping them around, flipping it vertically, and then also rotating it clockwise or counterclockwise, so that you could flip it all the way upside down or 270 degrees or something like that. Okay. But what about character arrays? What if I put characters into my array? Like H, E, L, L, O. What does that give me? A string, exactly. Strings after the midterm. Right. So what we're going to do next is some tooling, right? Including profiler which is going to be a static analysis tool, and debugging, and a proper debugger. Now I'm going to show you GDB, but I do think that they've got a visual debugger over here in the CS50 IDE where you can open this up and look at the call stack. I've not played around with it yet. I'm sure that you can. Yeah, there's a breakpoint. Let's go ahead and. I don't see a way of playing though. How do you? I'm gonna have to figure it out if you want to use this this online debugger here. I'm sure that there are videos out there anyway of it, but I'm going to show you GDB, which is probably just this is probably just a graphical user interface on top of GDB. GDB is GNU's debugger, GDB debugger, so GNU's debugger, and it basically allows you to load up a program and not run it all the way through, but you can stop the execution of the program and go line by line to look at, and you can examine the values, you can resume the program, you can say, go ahead and run it until line 100 because I don't want to have to go through 100 steps to get to where I want to be because I think that the bug is down there, right? So I'm going to give you a demonstration of that. I'm going to give you a demonstration of a profiler where you can detect memory leaks, and maybe a couple of other tools to round out the week. Next week, of course, on Monday, will be a review. The review for the midterm. The form that will take is we will live stream on Monday, a week from today, and we will hold a session here in Henslick. I will bring it last year's midterm, and we'll do it live. Right? And then, of course, on Wednesday, a week from this Wednesday, is your midterm, and all the details have already been posted on Piazza about that. We'll release it in the morning. You'll have all day until midnight that night to do it. No lecture on that day. No live stream on that day, but we will answer questions on Piazza and on in the office hours, but not to the extent that we would for a lab or a hack. Okay? No collaboration at all on the midterm or eventually the final. We will be running MOS, the Measure of Software Similarity tool, to detect plagiarism. It's supposed to be a test of how much you've learned yourself without collaborating with others. Okay? All right. Any more questions? All right. So when we come back next time, I will give you some demonstration on some tools that you're going to find very, very useful going forward. Now that we have established enough of a substantial programming background that these tools now actually become useful. Up till now, you've been doing some simple programs where you really hadn't had to debug too much yet because everything was pretty obvious, at least to a trained eye. But things are going to become way less obvious from now on, and you will need tools to be able to figure stuff out from now on. Okay? All right, see you on Wednesday.